There we go. Now we're recording. All right. So we talked about energy last time around, and we basically went through all the reasons why fossil fuels are so bad, although we're using them a whole lot. You guys remember what were some of the issues with fossil fuels?
Well, isn't it? Are you talking about the hidden costs?
Yeah, we have the hidden costs,
Yeah,
right?
we had the. I mean, hidden costs is like workers that may contract like illnesses such as cancer. Like coal miners have, I think what's called like black lung, uh, something like that. We also have like the methane emissions from natural gas. Also like the wastewater when you extract oil as well, that can contaminate. So
Okay,
that's
so
some of the issues.
pollution certainly is
Pollution.
one, right? They're both just standard air and water pollution, and also the greenhouse gases. What else did we say was difficult? There was one that's a little more obvious when we talk about the concept of fossil fuels, and the other one is maybe not quite so obvious. How many, when we talk about something that's a fossil, do we produce a whole bunch of new
Oh
fossils
no.
all the time?
Well, yeah, the fossil fuels are finite, that we're gonna run out eventually.
We're going to run out eventually, and that eventually is maybe not that far away. The
Mhm.
other thing I talked about was the concept of that most of our fossil fuel electricity generation happens at very centralized big power plants. That can be a risk because if something happens to them, right, we can have massive power outages. Whereas if we had a whole bunch of small ones, then maybe it happens like me this morning that I didn't have power for an hour and a half, but that would be a relatively small group instead of like the entire northeastern US or something. So those were some things. We also talked about the idea that we're going to be needing more and more and more electricity and energy because a lot of the people that are now using very little energy, we're hoping to bring them up to a living standard where they're most likely going to need more energy. Hopefully, not as much energy as we're using right now in the developed world, but more than they're using right now. Right. So those were kind of the ideas that we talked about. And then we said, of course, we don't like fossil fuel. Why do we use them? Right? They're cheap. We already talked about the external costs, right? So the external costs are not being paid by the producer, but by the consumer in the end, and by everybody else. And then the governments pay a lot of subsidies to keep these things going. All right, so that's where we kind of finished off last time. So now let's go and see what we can see in nature and how that is maybe better than what we currently are doing ourselves. So a couple of things that we want to think about as we're deciding we want to do this better, right? So one thing that we want to do is we want to change, right? We want to go away from fossil fuels, right? So we want to have an energy mix that is renewable and hopefully zero carbon, right? Ideally, it would be negative carbon, right? So we're producing energy that swallows up more carbon than it emits. Now, this is a little tricky. That usually doesn't happen, right? But we can put our thumb on the scale there a little bit and do some other technologies to get more carbon dioxide out of the air, but it's relatively expensive and it takes a lot of energy to do that. Right. So if we do these changes, then we basically have fixes for climate change and the concept of them being non-renewable, right? Because sun is and wind and all those are renewable resources. And also the centralization problem goes away because usually we don't have facilities that produce megawatts of electricity from solar or from wind. Right? So from geothermal could be a little different. Hydropower is also a little different. We can have very big power plants there. Another thing that we want to do is we want to increase the amount of energy that people can use. And the best thing that we can do there is we can create energy sources or we can use our energy in a more efficient way, right? So that would kind of help with the increased demand, right? If I can get the same standard of living using a quarter of the electricity, then why not do it? And this also, like, efficiency is always a good one. Even people who are not interested in the environment tend to like efficiency because, of course, if I can run my whatever, my car manufacturing plant with only 3/4 of the energy that I did before, then that's a lot of cost that I'm saving, right? So energy savings are usually also cost savings. And then of course, we would like to find new energy sources, right? What else is out there that we can maybe use? And there's some bio-inspired ones that are going on. And of course, my favorite one, since a long time, is what's called general fusion power. This is a technology that, if it were ever to work, would basically solve many of our electricity problems. It's very powerful. Basically, it's what's happening inside of the sun. It does not produce a whole lot of radioactive waste. A little bit it does. The facilities tend to become active, but there's no waste that is produced during the operation of these. Now, the problem with these systems until now is that they are not very good at producing energy. I think we've now gotten to the point where the first facilities are actually producing more electricity than it's needed to run them, right? So because you need very high-powered magnets to keep this kind of environment in place that is good for fusion. And even the ones that are able to produce energy, right, they're producing a very, very, very small fraction of what they need. And they do that for a very short amount of time, right? So certainly not something that we can actually build. And even if we did build these would be extremely expensive. Now, I like this because this is a great solution if it works. But the people who work on these projects have been saying for a long time that the finished product or the breakthrough will happen in about 20 years. Now, I've been around these people for more than 20 years, and they keep on saying it's about 20 years from now that this will be commercially available, and hasn't happened yet. And it's gobbled up a lot of billions of dollars in government funding to get these things to work. But again, if they do work, they'd be kind of our get out of jail free card to some extent. So certainly worth exploring. All right, so how does nature do it? We're going to look at 4 different kind of aspects of energy. We're going to talk about solar energy, wind energy, talk about liquid fuels. For those of us who don't want to drive electric cars, there's a fuel there that we can use. And then also the small scale storage of electricity. Let's start with solar energy. Everybody's always happy about solar energy. Of course, we have photovoltaic. We've had this technology for a very long time. This is not something that's new. It's been out in space for decades, like 60s and 70s. They were used with satellites because, of course, they're a great energy source for them, especially up in space where you get a lot more sunlight than we get down here because there's no atmosphere. We can directly get energy or electricity from solar light, which is of course great. The prices are dropping and dropping and dropping. They're lower than they've ever been. By now, they're not just cost competitive, but they're often out competing other energy sources on like the amount of money that you'd have to invest to get electricity, right? If you take the amount of investment, dividing it by the amount of electricity that you get, then basically solar panels tend to win out on that. But we have to also recognize that we do need a lot of resources to build solar panels. Some of the resources that we need, things like silicone, right? That's why the solar panels are this kind of bluish colors, because those are the silicone wafers. We also need silicon to build computers, right? So there's only so much high-grade silicon out there. So there's a little bit of a competition going on there, right? And also we have some other materials that we might need, and some of those are not so great as they're toxic. Now, another problem that we have is that the problem of disposal is relatively unsolved. And the reason for that is that we really started using a lot of these over the last maybe 20 years. And so these are all designed to hold up 20 to 30 years. So we haven't really had to dispose of a lot of them, right? Some of them, of course, right? But relatively small numbers. So it's not entirely clear how we'll deal with a lot of these used up solar panels, because they do degrade over time, right? They don't keep their efficiency forever and ever. So how are we going to recycle them? What are good systems that we can put in place? And of course, now we have to think about how can we design these in a way maybe for the future where they're easier to recycle, because if we're going to have a lot of these, we better build them in a way that we can disassemble them. Another thing about solar panels is that they're not even close as efficient as photosynthesis, right? Photosynthesis grabs about 100% of the energy is transferred, or 100% of the energy that's captured is transferred into energy, into chemical energy, whereas good solar panels, well, by now they're over 20, right? They're maybe 25-ish in their efficiency. So they're getting better, but they're nowhere close to what photosynthesis is. Also, it's important to remember that although we always talk about kind of photosynthesis being the bio inspiration for photovoltaic, it's not really the case, right? Those are two very different concepts. The way that photosynthesis happens is very much different than the photovoltaic effect, right? But from an abstract standpoint, they're similar, right? Sun shines onto something and that produces electricity or chemical energy for the photosynthesis. All right, so let's have a quick look at photosynthesis. And I would have to be the first one to admit that I'm no expert on all these little chemical transitions and how electrons are moving through the system. But in general, we can say that the solar energy, when it hits the place, like what we call the chloroplasts, once they hit those, it basically splits hydrogen and oxygen apart and has some electrons there as well. And so then this hydrogen and the electrons are kind of moving through this entire complex system until they're used to then build ADP, right, which is kind of the internal energy source that the plant uses, right? That's kind of the chemical storage. You can think about it as a sugar or something, right? So that's where the energy goes. So overall, this very complex system takes solar energy and turns it into chemical energy. Now, we're usually not that interested in chemical energy, right? I mean, I guess we can say we are, because this chemical energy, of course, is then something that winds up in our fossil fuels, or if we burn wood or something, right? So we kind of use up that chemical. We can use the way that way, or of course, if we start eating salad or something like that, right? Those chemicals were taken in as well, right? So in that way, but like from an idea of producing a lot of electricity, this is not quite the way that we want to go. But there are people who are looking at exactly that, right? So there's research groups that are basically trying to take that electron that gets split off, and somehow capturing that. And like, of course, if you have electrons flowing, right, then you have electricity. That's all electricity is. Now, the difficulty right now is that when you split off those electrons, they want to keep on going through the entire system and then creating ADP. They're not interested in splitting away. And so basically getting them to split off, and then in this case be transported along carbon nanotubes, has shown to be quite difficult. But it does work, right? I mean, they can produce currents based on the system, but they're still very low. But we have to start somewhere, right? Maybe once we figured out, like now we have very low, but as we work more and more, maybe we can find something that is that's more effective. And of course, that would mean that we have a much higher efficiency. Now, what would be the good thing about having a higher efficiency when we think about our solar panels? We still call them that.
Well, if we have higher efficiency, doesn't that mean we can use less? Or we can use less to produce more?
Less space for solar panels, more production of energy at the same time.
Right, that's the idea, exactly, right? Is that we would need less space, right? A lot of people complain about all the space that's being used up by solar plants. I'm not sure. I'm one of them. We're not using all that much space, and like a big coal-fired power plant tends to take up some space as well. It's just a little more concentrated. But if we could reduce it, right, then we wouldn't need as much land surface. And of course, if we have very high efficient solar panels, right, we can start thinking about having an electric car that is plastered with those solar cells, and maybe it's producing enough electricity to keep my car going, or at least to reduce the amount of time that I have to stop and plug into a charger, right? So those are all things that if we can make that small enough, it will work. All right, another way that we use solar energy is with what we call concentrated solar. Basically, what it is, we have a whole bunch of mirrors that are all set up in a way that they concentrate the light up into one big tower. Up in that tower is some way of collecting, of passing a liquid through there. That liquid gets very hot, or oftentimes doesn't start out as a liquid, but it's a semi-solid. We do this a lot with salts, right? And so these salts basically evaporate and then go through the system, and we can use them the same way as we would any other thermal power plant to produce steam that then runs through a turbine and produces electricity, right? So these are systems that are in place. There are a couple in the US. There's a couple of really big ones in Spain as well. And basically they're a very clean way of producing electricity, right? Because remember, all these like shiny surfaces you don't see down here, they're just mirrors. They're not photovoltaic cells, right? So sort of just like a very highly polished metal usually. So yeah.
Bird incinerators.
Yes, well, there's always negative impacts, right? We just have to keep the birds away. But there's ways to keep the birds away by inspired ways. Well, I guess it's not birds, it's bats, but we can probably think of something that works for birds as well. So one of the downsides is, of course, that they have a very large footprint, because these are very massive systems. That's why you usually see them sitting outside of nowhere, in the middle of nowhere somewhere. But people have figured out that they can actually reduce the footprint of them if they put these mirrors basically in the same pattern as we have on the inside of a sunflower, right? So these little petals on the inside of the sunflower aren't there by randomness. They're trying to get sunlight to do their thing. And so, you know, the better this pattern is, the more of these little petals I can have. So people looked at that and they converted that into kind of a setup that they can use to put mirrors down for a concentrated solar plant. And they noticed that they can reduce the size and at the same time increase the output of the plant, right? So it's a double win. And you can see, of course, here, this would be south, right? Because you have all this area here where we don't have any mirrors, because they wouldn't be able to reflect any light back. Because if the sun is coming from there and my mirror is sitting like this, right, then it's hitting the back of the mirror. So there's no way of reflecting the light there. So that would be south. But these work, right? And these work really well, even if it's a cloudy day, right? It doesn't have to be bright sunlight to do this. Of course, if there's bright sunshine, it's even better. That's one way of using bioinspiration for this. Another way is that, of course, we all have learned in middle school or even earlier, right, that plants will move with the sunlight to kind of keep them oriented towards the light. That's especially prevalent in sunflowers, right? Especially because we'll have the very long stems. So we can see that happening during the day, and then during the night they kind of swing back to where they'll be needed in the morning. And we can do the same thing with photovoltaic systems, right? So we can basically build solar panels that are always optimally oriented towards the sun, right? So basically they're on a little platform turns, and the panel is always facing the sun. Now this is great, it's a cool idea, but we have to be a little careful with that. We have to make sure that the extra electricity that we're getting from always being faced towards the sunlight does not get eaten up by the amount of electricity that we need to power this, like the rotation and the sensors and the computation that are going, all that kind of stuff, the controllers, right? They will all take electricity. So if you can get rid of that benefit very easily. But you can buy little little plants for little lights that you can put in your garden that will do that. They don't really do it for added efficiency. They really do that more just to look fun, right? Which is always important. All right, so that's kind of the bio-inspired ideas that that I could find that are related to solar power. Now let's go to wind energy. That's always a good one. It's becoming more and more important in Costa Rica. And if you ever go to the campus in Lubbock, you will see how important wind energy is there. So the one I've only been there once, but when I was flying in at night. And so like even like so 20 minutes from the airport or something, right? You can see these big areas of like basically darkness and then a little flash of light, and they're all flashing at the same time. And that's at the top of the wind farms, like to keep the birds away or keep the planes away, right? Basically make sure everybody knows that there's something there. Look very spooky, right? But there's a huge amount of wind power installed in Western Texas because it's flat and it's windy, right? And so the very conservative state of Texas is one of the leaders of renewable energy in the US just because they have that resource and they've noticed that, hey, this is cheaper than burning oil that we're producing. We can sell that oil to somebody else, right? So wind power is becoming very important, and I think it's going to get only more important as time goes on. So let's talk a little bit about bio-inspiration for wind power. Now, this is strange. We're talking about wind power, and the first thing I show you is an animal that lives in the water. Has anybody been whale watching out down in the southern parts? I haven't, but something on my list to do. Anybody been out seeing the humpback whales slowly move by? I don't know. Something to do next time you're in that area. But the reason why we talk about humpback whales here is the way that they catch their prey. All right, so humpback whales are massively huge, right? There's like a little school bus up here for scale. Of course, the food that they eat, krill here, is not the scale, right? This is much smaller. They're little tiny kind of shrimp-like things. And so if you're this big humpback whale, you can imagine you need to eat a lot of that stuff to be able to survive, right? And so just swimming around all day with your mouth open is not enough, right? So you have to somehow concentrate them all together in one little space so you can actually eat them. Basically, you have to catch them. And the way that they do is it's quite amazing, right? So these humpback whales will swim in tighter and tighter circles, and as they're doing that, they're puffing out air through their blowhole, and that air basically acts like a net. So all these little bubbles that are going up are basically the krill don't want to be in those little bubbles, right? So they are going to swim away from that bubbles, and so the ones that are kind of in the middle here, as these rings get tighter and tighter, like they're going to get more and more concentrated because they're trying to get away from those bubbles. And so once the whale has a tight enough net, I guess you can say, it goes down and then comes up through the middle and the mouth wide open and just has it open and all the krill get caught. Right, that's the way that humpback whales, or one of the ways that they catch it. Up here in the picture, you can actually see two of them working together, right? You can see two lines of bubbles going in, and then they should be coming up pretty soon. They're somewhere down there, right? Very, very impressive thing. Now, why is that important for wind energy? Well, it turns out that if you're this big of a whale and those turns are quite tight, those are not wide circles, these are small, right? This is kind of, you can see here in the scale, right? This is, the center of this is going to be maybe the width of a whale's mouth or something, right? So it's a big mouth, but it's still not very big, right? And so if it has to swim at very tight circles, and that's not easy to do, because the way that a whale steers is the fins, right? It has these big long fins, also called, I guess the back ones are all flukes, the front ones are just fins. And just like with anything else like this, if you so the water is coming basically this way because you're swimming through it. If you go too steep against it, then basically the water breaks off, the flow breaks off, and you get a lot of turbulence. And once you get all this turbulence, you just can't steer anymore, right? You lose control basically. And so people have started looking at how whales do this. And it turns out that these weird bumps that they have on their fins are actually massively important, right? The reason why they can do that are these bumps. And just because you can't make it up, the guy who researched this is Dr. Frank Fish. I don't know. I'm not sure if he changed his name or if he decided to go into fish because of his name, but that's what it's. So the thing is basically that these little ridges that you see on the fins here basically allow the flow to be what we call laminar for a longer time. Laminar means when the flow is nice and organized. If it's not laminar, it's turbulent. Once it gets turbulent, it doesn't help you steer a whole lot. You lose a lot of energy in those little kind of whirlpools that are happening all the way when you have turbulence. And so what people found out is that they can take that and they can basically make these humpback whale edges on wind turbines, on the blades of wind turbines, and that increases the efficiency by 20%, right? 20% efficiency increase is not a small number, right? And it's not, you don't have to do a whole lot to do this, right? So it's not going to be, obviously it's going to be more expensive to do like a serrated edge than a flat edge, but it's not that much more complicated to do, right? So you can really get a big increase in efficiency by the small change, right? So this is something that's very, very interesting. So you'll see more and more of these serrated wind turbines. Has anybody ever stood underneath a wind turbine or been close to one? If you haven't, you should find a place to do that. They are huge. Like when you see them, like the ones that are up above Santana, right? They look kind of small, right? But if you really get up close to them, they are massive, right? These single blades, right, are usually too large to transport on a regular truck. They're too long, right? So you have specialized trucks that move them through the countryside. It's incredibly how big they are. It's really something to see. All right, another thing for blades is the noise, right? So when you're close to a wind turbine, there is some level of noise. Now, I don't think it's all that bad, but like, maybe if you live really close, it might be an issue. Now, I know my sister has never complained about it. She lives up in northern Germany. The county that she lives in has the highest density of solar power in the country, of wind power, I'm sorry, in the country. There's more wind turbines than people up there, right? So and she's never complained about the noise, but who knows? But it does produce some level of noise. And so people, of course, want to reduce that noise. And so they looked into nature and they looked at, well, where are things that are moving very quietly? And as some of you already found out, because you had that in one of the projects I saw this, people realized that, of course, owls are very quiet when they fly down to catch their prey. Right? They have to be, because if they're coming down with a huge amount of noise, then the prey is going to run away, right? So you have to obviously evolve into a way that you're very quiet as you're dropping out of the sky to grab, in this case, this poor little mouse. In this case, the owl looks very, very threatening as it's coming down there. And what people found out is that the leading edge of those feathers have these little kind of hairs, you can almost say, almost not hairs, but they're just part of the regular feather, but they're coming, this leading edge has these little tips coming off of it. And these little tips actually make the movement around that slightly different. And for these big wind turbines, people found that they can reduce the noise level by 10 decibels if they do that. And 10 decibels is a significant amount, right? That's something on the order of my speech here or more, right? So that's really, that does make a large difference, right? So we can have wind energy that produces less noise. So now we've made it more efficient. We said we reduce the noise. What's another thing that always comes up when people talk about wind turbine, when there are people that don't like wind turbines? Not that many in Costa Rica, so maybe it doesn't come up that much.
Is it like maybe birds flying into wind turbines?
Birds, right? The bird killers kills off all the birds. Now, I have to say, from again being around wind turbines, I don't usually see huge amounts of dead birds lying around, but I might have just been lucky. But that is in general that is a problem, right? Even if it's a small amount of birds, not only obviously is it not good for the birds that are flying against those turbines, but it's also really not good for the turbines themselves, right? To be striking birds at any level. And now with its birds, people have gotten really good at getting birds away by using certain types of lights that are on top of those turbines, and that really help keep birds away. But one thing that does not keep away due to those lights are bats. So there's a fair amount of issues with bats smacking into wind turbines. And so people went out and tried to figure out, well, we came up with these lights for birds. What can we come up with for bats? And it turns out there's this little moth, much smaller than the picture here, of course, right? It's called a tiger moth. And that tiger moth has developed this great capability. It's amazing. And that is that it's basically running interference, right? Remember that a bat uses echolocation to find its prey, right? It's sounding out a sound wave, it's sending out a sound wave. And when a sound wave comes back, it knows that's where my little critter is that I'm going to eat. Now, these tiger moths have figured out a way how to send out a signal as they're buzzing around that basically interferes with the sound waves that the bat is sending out. So the bat is not getting a clear signal back, so it's basically confused, right? This is something that we were very proud of when we developed that during the Second World War with the concept of interfering with radar to stay hidden, right? But these bugs have been doing it for a very long time, of course. And so people have done studies, and if you look at the picture that you see down here, they're basically taking that same concept, and here these kind of green dots are basically they tagged a whole bunch of bats and followed them around this little pond area, and you can see they're moving around quite a bit, and there's a whole bunch of them. When they turn down their little sound generators, that's the next one on here. This is where it's on. You can see there's hardly any, right? And so just by putting that sound there, and it doesn't travel all that far, so it doesn't mean there's no more bats in this entire area. It's just where this sound is happening. And so people have installed these kind of sound generators on top of wind turbines, and they've seen that bat fatalities drop by up to 50%, which is great. Right? I mean, it's like be good if it dropped by 100%, but you have to start somewhere, right? So these are all different ideas that we can think of when we're thinking about wind energy. Now let's come to liquid fuels. So liquid fuels are still very important, right? Most of our transportation relies on liquid fuels. I think we're at the point where we can say that certainly light vehicles are going to be relatively easy to switch from a combustion engine and liquid fuels to electricity and batteries, right? So we have cars, we have scooters that are only going to get better. But there's other forms of transportation where this doesn't work so good. So this doesn't work so good for
aerospace,
for air, like any planes that we have, and also for cargo ships. This is not something that works very well. Now, one place where it works perfectly in transportation is, of course, trains. Right? We've been using electricity in trains for decades, right? That's nothing new. Not so much in the US, but almost everywhere else in the world. So how can we come up with liquid fuels that are not hydrocarbons, basically? Well, one way, which is not really biomimicry, it's more bioutilization, is to create what we call biodiesel from algae, right? So we basically create these hard hydrocarbons, not from fossil fuels, but we have little bacteria and algae that kind of do the same thing, and we can use that. And there's a fair amount of research going on that is funded by the military because they want to get a jet fuel that they can use that they can basically grow on site, right? Because then you don't have to worry about any kind of supply routes being blocked by your enemies because you're producing it close to where you need it, right? So there's a big push for that. And I'm not sure about this type of biodiesel, but there's a second type of biodiesel that people produce, and that is based on old, on used up cooking oils, right? So if you run a restaurant and you create French fries or something like that, right? Then you have to switch out that oil every so often, and hopefully a little more often than some places do. And there's places that can take that oil and then basically turn it into a liquid fuel, also called biodiesel. And the fun thing with those biodiesels, often, especially with the older generation of those systems, is that if you have a truck driving in front of you that is burning that type of biodiesel, it smells like they're making French fries. So it's like you're driving down the highway and all of a sudden it's like, man, I'm hungry. I need some French fries. Right? It's a very distinct smell. But this is not really biomimicry, it's more bioutilization, right? We're using a different type, but it still gets us where we want to go. Now, one thing that is kind of still in developmental stages, but hopefully we'll be able to overcome the issues, is basically to take photosynthesis and create hydrogen from photosynthesis, right? So at the moment, when like in a plant, right, photosynthesis creates ADP, but we can couple the process of photosynthesis with a special enzyme that basically turns the result into hydrogen, right? So we could have just a bunch of greenish liquid, and it kind of, when the sun shines on it, it will start bubbling out hydrogen. Of course, hydrogen is a liquid fuel, right? We can use liquid hydrogen to run our cars if we wanted to. Now, hydrogen has a little bit of a bad name in transportation. Anybody remember why people kind of don't like to use or are worried about hydrogen?
Because of airships.
Exactly, right. The famous Hindenburg disaster, the humanity, right, of people dying in that I mean, it was a massive disaster, right? Kind of killed the whole idea of using hydrogen for a long time. People are kind of coming back around to hydrogen more and more, because of we can use it to produce electricity through power cells and all that kind of things. And people also kind of start remembering that gasoline is not the most stable of all liquids either, right? It likes to burn and it likes to explode, right? So it's not totally benign. But so we could use this to again get hydrogen directly from photosynthesis, which would be great because it's going to be very efficient. The other great thing of using basically a living organism to do this photosynthesis and get our hydrogen from is that living systems repair themselves, right? So if you have anything that's going wrong, right, if some of the cells are dying off because, I don't know, too much sunlight or something, some contamination, right, other cells will be there to regenerate. And they grow, right? So it's not, I can grow more and more and more than I wanted them, right? So usually we have the issue of too much growth versus too little growth, right? So this is really something that's very, very promising. And as I was saying, right, the idea is that we could use these to power fuel cells, right? So a fuel cell is basically a system where you bring in hydrogen and oxygen, and they kind of the way to, it takes the oxygen combined with hydrogen, right, turns it into water, and that process basically drives a current, right, because the oxygen is going, the oxygen ions are going through here and changing the charge. The great thing with that is that, of course, what's coming out of your tailpipe is water, right? It's probably going to be gaseous water. It's not like I'm dripping water out, but it is not carbon dioxide and a whole bunch of other nasty stuff, right? So it's something that we could have very clean fuel. And the advantage versus batteries is that, of course, it has the same quick refueling time as a combustion engine, right? So one of the things that is holding back electric vehicles is the charging time, right? So that limits kind of their useful range, because if it takes several hours to basically refuel your car, then that might not be useful for something like a long haul truck driver or something, right? Who needs to be on the road for a very long time, or here in the US, if you want to do a coast to coast road trip or something like that, right? So that'd be more difficult. But if you had hydrogen, right, you could do that. You just drive up to the next hydrogen station and plug in and go. If there were any hydrogen stations, right? It's of course part of the infrastructure that we'd have to build out. Now, another way that we can use solar power basically to create hydrogen is what's called an artificial leaf. So basically it works the same way that photosynthesis does, where it's kind of breaking apart water, HO2, right, due to sunlight. And it's like the two kind of areas which happens, there are two catalysts, and then there's a separation in between to make sure that the electrons just don't go from one side to the other. And so when you do that, then basically you are again producing hydrogen, right? Hydrogen over here, right? And so as you can see in the little video down there, if it plays, there we go, right? Is that you have these little that look like little plates, and as the sun shines on it, you can see the hydrogen slowly but surely bubbling off of them, right? So all we have to do is have them sitting in water, and then they're producing hydrogen without anything else going in. Of course, you have to capture to hydrogen and all those kind of things, but we can then take that hydrogen and stick it into a fuel cell, right? So that's something good. Again, has the same operating procedure as photosynthesis, which is different than the photovoltaic effect. So that's what's called an artificial leaf. And we can take that one step farther, and that is, so this is our regular leaf, right, where we kind of doing the photosynthesis. This is our artificial leaf, right, where the same thing is mostly going on. We get our hydrogen, but we can combine that into what is called the bionic leaf, like kind of a bionic man. So better than a regular man, like better than a regular leaf. And so we're adding a special type of microbe that basically eats the hydrogen and turns that into methanol, or another type of what we call syngas. And of course, those we can use very easily in combustion engines, right? So we could basically have something where we produce these liquid fuels based on the CO2 in the atmosphere. So we're taking CO2 out of the atmosphere to produce our fuels. Then we stick that into our cars, we burn it up, goes back into the atmosphere, and we have a nice little loop, right? So that'd be a very renewable way of doing that. Those were our bionic leaves. Now let's see what else. Well, that is the concept of capturing CO2 from power plants. Now we all probably are aware of the idea, right, that if I'm burning coal or if I'm burning gas, then a lot of the stuff that's going out the top of my chimney is going to be carbon dioxide. And one approach, one idea is to basically, before that CO2 goes out the smokestack, you grab it and you take it and you squish it together and you pump it deep underground, right? Which is called geologic carbon sequestration. And if you don't stop me, I'll start talking about geologic carbon sequestration for the next 2 hours, because that, for a very long time, was one of my main research projects that I was working on. But one of the big problems with all this is the capturing part, right? Is to basically get the CO2 out of the smokestack before it goes out. And there's a lot of chemical processes that you can do, but those chemical processes come with the problem that to basically you kind of have an absorbent that the CO2 goes through, and then to get the CO2 off the absorbent, you need a fair amount of energy. And so if you run a capture plant, it will basically steal about 10 to 20% of the electricity that you're producing, which is of course not very good, because so you need more electricity, which means you're producing more carbon dioxide. And so how do we do this in a more efficient way? And one of the ways that people are looking at are our lungs, right? Big part of our lungs is, of course, getting oxygen out of the air into the blood. but it's also getting the CO2 out of the blood and into the air, right, as we're exhaling. And it turns out we're actually very good at doing that, right? Those systems work very high efficiency, and they're also working at relatively low concentrations, right? So we can't do this air capture in the normal air because there's not enough CO2 in there usually, right? So it becomes very difficult. But if we can devise systems that work the same as our lungs, right, then we could get a lot more capture. We can get a lot more CO2 out of the air, which means that we can turn back our climate clock a little faster. And so turns out that this can become very effective and capture up to 95% of the CO2 at relatively small energy costs, right? So it'd be a very cool thing to do. Now, just to point this out, of course, the most of what you see in this billowing smokestack here is going to be water, right? It's going to be steam. So those always look a little more impressive than just where the actual CO2 is coming out. All right, now the next one that we're going to talk about is the idea of storage. I think we're all aware of the idea that as we're building out our renewables, we tend to have storage combined with them because, of course, wind and solar don't work all the time, right? The sun doesn't shine during the night and wind doesn't always blow, right? So we have to have a way of storing electricity. And of course, even if we didn't do that, we still need to store electricity because we're all walking around with little cell phones, right? And it always sucks when your battery's running out when you need it for something, right? Of course, it always runs out when you need it most. Now, the prevalent type of battery that we have are what are called lithium-ion batteries. And what's great about these lithium-ion batteries is that they have a fairly high, what we call energy density, right? So the amount of energy that can store in a given volume is relatively high, and we can recharge them, right? So it's not that I get the charged battery and then I use it and then I need a new battery. I can keep on, we can do it. There we go. A whole bunch of them right there. If you can see on the Robert's hand with all the cells in there. So the ones in his car are probably just slightly bigger, but they will work as well. And so basically how this works, you have the cathode, you have the anode. The red little dots here are lithium ions, and if you're discharging the batteries, then basically the ions are going through this little separator here onto the other side. As they're doing that, they're transferring charge, which means electrons have to kind of flow through to the other side, and that's like we're using that electricity here. Now, if we've discharged it to an extent where we can't use it anymore, then we can just reverse the thing, right? We could put our charger here that pumps electrons in there. That means the charge changes here, which means that the lithium ions want to move back to the other side, and we can do that again. Now, theoretically, we can do that forever and ever and ever, but as the world goes, right, nothing is theoretic. Everything is practical, and as we all know, right, sooner or later, our cell phone batteries don't work as well anymore. And there's all kinds of things that you can do to keep them going for longer. But even if if you're really careful about them, they will still lose their capability of keeping charge. And although they have a fairly good energy density, right, we still need a pretty big battery in our phone, right? So by my phone here, I would assume that maybe a quarter or something like that of the weight that I have in my hand is probably the battery. And it's lasting maybe like a day and a half, something like that. Just imagine you had something that's 10 times smaller and lasts 10 times as long, right? So you had teeny tiny battery that you have to charge once a week or once every 2 weeks, right? That would be kind of cool. The other problem is that, of course, we're using lithium and some other stuff in there that tends to not be so easy to get or tends to be not so healthy to be around, right? So those are things that we have to think about. So one thing that we can do with our lithium batteries is basically to replace the lithium, right? So the stuff that's in there, and to replace the structures that are inside that are holding the lithium. And so what people have found that they can create carbon structures that have similar efficiency as our engineered materials. And basically where they get these carbon structures from is they look at pollen, and they kind of basically burying them, right, then you get these carbon structures that work very well. Now, the cool thing about this research is that it's actually one of the few solution-driven examples that we have, and that is there was this researcher who got really interested in pollen and why they create so much difficulties in humans when they get allergies, because his mother developed a massive pollen allergy, and so he wasn't a medical doctor or something, right? He was an engineer, but he was just interested and did research on them, and then at some point later on realized when he was working on batteries that the structures of these pollen were very similar to what he was seeing in the battery designs. And so they started working on that, and it works great. All right, so that's one thing that we can do. Another thing that people have looked at is to basically change the chemical composition. So instead of having just lithium batteries, we can do lithium sulfur batteries. And the great thing about lithium sulfur batteries is that they have a higher energy density, right? So I can put more energy into the same volume of material, which is great, right? If you think about a car, right? If you could get more energy into a cell that weighs the same amount, right? Then you're moving around less mass, so you can use more of the electricity to move you forward, right? So that'd be a great thing. Now we have these lithium sulfur. It's a tough one. Batteries, they are great. They have this one really big problem, is that they degrade very quickly, right? But I said the lithium ion batteries that we have, right, we can recharge a bunch of times. At some point, they start to kind of wear down. Lithium sulfur batteries do that very quickly, right? So we have to come up with a way to do that. Basically, what happens is the lithium start, or the sulfur structures, basically as they're charging and discharging, part of the lithium gets stuck in them. And so kind of it fills up the space that they could move around in otherwise. And so people have kind of looked around nature to see where we see these kind of structures that are similar to those sulfur structures in the batteries. And they found these nice little things. And these nice little things, this is an enhanced photograph of the inside of your intestine, right? So you have these little polyps sticking out that are basically there to absorb the nutrients as the food is going past, right? And so it turns out if we build lithium sulfur batteries that have these structures inside, then we can keep the batteries from degrading, because the stuff just kind of trickles down, doesn't collect as much, right? And so that means we could build batteries that have five times more storage than the standard lithium ion battery, right? Which is a big thing. Again, think about only charging your battery every week, right, instead of every day. Or think about a car driving now 5 times more than it could, like an electric car, right? So at the moment, I think we're around, was it 300 miles or something like that of radius that an electric car can drive, right? Now, if we turn that into 1,500 miles, right, then that's no longer a discussion, because nobody's going to drive 1,500 miles in a day, right? So that's something where it'd be enough to then just recharge the car overnight, right? So that becomes a big difference maker. Another thing that we have is what we call supercapacitors, and that is the idea of building capacitors. You kind of see it here a little bit, that are based on the kind of very intricate structure that we see on the leaves of ferns. And of course, there's almost no place that has as many ferns as Costa Rica. It's amazing. I remember going up into the hills above Coronado once, and it was amazing to see that the entire flora changed, right? So like you have kind of pine trees and palm trees like farther down, and cypress trees maybe, and up there was all ferns. Right, so there were basically ferns that looked like trees. They were so big, right? But it's still ferns. But that is completely aside, right? But they have these little leaves that have like more or less a fractal structure, and you can see kind of this capacitor trying to mimic that. And having this structure increases what the capacity is, and actually going to increase it by a factor of 30, right? So you have all of a sudden you have a lot of energy that you can store in these little capacitors. And it also kind of holds on to that charge longer, right? If you put electricity into a capacitor, it's not that the capacitor degrades over time with being charged and discharged, that's not the problem, but it basically just, if it just sits there for a while, then the energy is going to be gone. Right? With these structures, it takes longer for that to happen. So now you can imagine if you have something, and you can see these are very small, right? So you can basically combine that with a photovoltaic cell, and you have an integrated system, right? Where you have the charging and the storage all together, and then you can discharge it whenever you need, right? So great if you think about, you know, the little garden lights that you have, or the little security lights outside, or street lamps, or something like that, right? So there's many applications that we could think of. All right, getting close to the end, which is good. I just have a couple more examples left, and these are just kind of things that I thought that were cool that don't really fit into any of these other categories, right? But are still are energy related. And the first one is the idea of getting electricity from waves, right? We all know that, like, whenever you're anywhere close to an ocean, there's always waves, right? And people have tried to harness that energy for a long time. It's really difficult to do, right? Because usually when we think about that, we think about the energy of the wave as it's crashing onto the shore, right? It's a lot of energy in there, but how do we get this out? And there's a group in Australia that basically built these devices that are anchored, so they're not at the surf, but they're a little farther out, where just the kind of the wave kind of goes back and forth. And they have built these devices that are anchored on the ground and that have floats. And basically, as the wave goes by, they kind of do this motion back and forth all the time. And so that motion then produces electricity. There's also ones that are sitting on the top, right? That kind of have joints in the middle, and as the wave goes by, kind of that up and down motion produces the electricity. Now, the good thing about these ones that are in the water is that they can easily change their direction to make sure that they're in the right direction of the waves, and they can basically just flatten down onto the ground if there's a storm coming through. Right? The ones that are floating on the water, of course, if there's a hurricane or something coming through, then they're going to be in trouble. I would have to probably get them off or do something with them. But these we can just flatten onto the ground, the storm goes past, and we have them back. It's of course great, because often, like, one of the big things that happens after a hurricane is that people lose power. Now, if we had something that close by, right, then we wouldn't be worried about that as much. All right, another thing that we have, where everybody has LEDs these days. And of course, we did a lot of research into figuring out how to get better LEDs. And so people looked at fireflies, right? Fireflies kind of create their own light, right, due to chemical reactions. And when people looked at kind of the little container, I guess you could say, where this light is coming from, then they see these very distinct structures on top of it. And so what they've done, they've kind of manufactured casings for LEDs that have these same structures. And it turns out that our LEDs shine about 60% brighter if they have these weird structures on there, right? So a huge energy savings. I mean, LEDs already are great because they use so little energy compared to incandescent bulbs, but that makes them even more efficient, right? Which is super cool, because we use a lot of electricity for lighting. And now, one thing that probably at least some of you, I hope, are directly familiar with, because you can see this in Costa Rica, right? You can go, swimming in the bioluminescence, and if you have never done that and you ever get the chance, right? If you're down on the peninsula, right? There's multiple different places that you can do this. It is amazing. It's really cool. I mean, I've never seen it reflect like this on the beach. I'm not sure how much this is a doctored picture. But if you jump, like when we went, like we took a boat out in the water, and you jump into there, and basically, like, each time you move, there's light around you. So it's very cool, right? And so people have just thought about, well, if these little critters can do that, how can we kind of take that and use bioluminescence to produce light, right? Just to use as lighting, so we don't have to use electricity. And so they've taken an E. coli bacteria, basically, and they've taken the genes for bioluminescent algae and implanted them into the E. coli, and then we're very clever about it and called it the E. coli instead. And so these work, right? You can basically have them sitting in a little jar and you shake it and the whole thing starts glowing. Nobody has really found a good way of using them. It's not a very bright light, right? It's not enough to light up a house. If you go swimming in them, you'll see it's not very bright, or you can see it because it's very dark, but it doesn't do all that much. But you could do all kinds of stuff with this, right? So people have thought about the idea, if we can incorporate these into trees or even better bushes, that we can plant along the side of like rural highways, right? Then just imagine you're driving down the highway and you can basically, for how far you can see where the highway is, right? If it's dark out and you're driving, right, sometimes a little hard to see where the road goes next, unless there's somebody driving in front of you, right? But if there's not a lot of traffic, then that would be great, right? Now, until now, it's not worked that great. One of the big problems they have is that they really have a difficult time of keeping these things alive. And of course, once they're dead, they kind of degrade very quickly, right? So it's something that we need to figure out yet. But it's one of those things, doesn't have a good application yet, but maybe we'll find one down the road, right? That's often the case that these systems work, is that you develop something and it doesn't have a direct application, but then 10 years, 15 years down the road, somebody sees the paper and is like, oh, it's exactly what I need. Let's do this. All right, then kind of coming back to what we talked about before, are these serrated edges. We talked about them for the wind turbines, right? But we can do the same thing and stick them onto the edges of the little fans that we have running in computers, right? And so if we do that, we can reduce the electricity demand by 12%. Right? Again, 12% first doesn't sound like very much. In the world of efficiency, 12% is already a huge amount, right? And by not doing anything much, right? All we have to do is slightly alter how we produce these little plastic pans, right? For the mold that these are pressed into, it doesn't matter if there's little serrated edges or not, right? That's not a big cost difference. But the other thing that we have to think about is that about 4% of electricity use in the world is used for computer cooling. Now, this is not all by little fans, of course, so it's a little bit of a stretch. But in general, so there's a lot of electricity being used to cool them. And if we can reduce that by 10%, right, that all of a sudden does make a difference, right? So that'd be 0.4% of the world's energy demand is gone, right? So that again doesn't sound like very much, but that's a huge amount of energy that we could save by just this tiny change that really doesn't make any difference cost-wise to the production. All right, I think that's all I had about energy. Last thing I have is, or the last two things I have is, remember to hand in your proposal. I saw there's already one group that has handed in their proposals. That's great. Everybody else, please hand it in tonight. And the other thing that I would like you to do, also the journal entry, let's not forget. And then I have another video for you to watch. This one is about basically materials. Right? So if you could do those two things, again, this is also linked on Blackboard, so you can find that video, or you can take a snapshot of the QR code right now if you want to. All right, any questions? So have a little time if people have some questions about about their proposals. If nobody has any questions, then I will release you and let you work to finish up those proposals and hand them in.
All right, thanks, sir.